Thank you very much for the introduction. Thanks for being back to episode 3. And let me just quickly remind you of what we accomplished last time. And so here's the main results. So we have encoded linear algebra problems in Quiver representations, and we have a categorical approach to Quiver representations. They form a nice abelian category, and a geometric approach to Quiver representations in an action of a reductive linear algebraic group, a product of GLs, or linearly on some nice vector space of tuples of linear maps. And then we have seen the first construction of moduli spaces last time using classical invariant theory. Namely, we have produced a quotient of the space of all representations by the base change group, which we call MD as sim of Q, because, well, it exists as an affine variety and it parameterizes isomorphism classes of semi-simple representations of the given quiver of dimension vector D. So this is the spec of the ring of invariance, and I've explained last time how in principle you can reconstruct it explicitly, and we have seen some examples. And let me point out again that here you see the interplay of the geometry and the categorical approach. This is a geometric object, an affine variety, which parameterizes isomorphism classes of semi-simple representations, semi-simplicity being a very nice categorical notion for objects in an abelian category. We have also seen that this variety is always irreducible and normal, affine, and it is of a known dimension, 1 minus sum over di squared plus sum over di dj along the arrows, if there exists a simple representation, which can be decided effectively. And we can also, in principle, find explicit coordinates for these varieties. Namely, the coordinates are given by traces along oriented cycles in the quiver. But that already told us about the main drawback of this approach to quotient. Namely, it only gives interesting quotients in the case where the quiver has lots and lots of oriented cycles. And the problem is, if we have an acyclic quiver, then we have a unique closed orbit in each representation space. And this type of quotient can only parameterize these closed orbits. And at the end of the last talk, I illustrated this with two very simple group actions of a multiplicative group on an affine plane. Look at this example for the action t times xy equals tx ty, just the dilation action where you have a unique closed orbit. But in a P1 family, namely all punctured lines to the origin, a nice family of orbits which we cannot parameterize with this construction, with the invariant theoretic quotient, because it only parameterizes closed orbits. And then the idea was to somehow get rid of bad orbits and only look at good orbits, whatever this means. And this is where we will start now. I will keep this theorem here because we will see somehow another version of this theorem, and then we can somehow compare it statement by statement and see why our new construction of moduli spaces of stable representations today is really a direct analog of this classical thing. Okay, so let's start with the new content for today. And this is section 3.2. As far as I see. So let's look at not the classical invariant theory of Hilbert, but of Mumford's geometric invariant theory in a simplified version, namely only for linear actions of reductive group on vector spaces. So let me briefly try to summarize Mumford geometric invariant theory for linear actions. I will tell you the basic idea how to get rid of the bad orbits, and then we will again apply this to the quiver situation. The application will not be as immediate as last time, so I have to omit some details, but I hope you will see the analogy. So we are given a linear action like last time of a nice algebraic group on a complex vector space. And we assume that G is reductive. And now we make an additional choice. And this is a choice you have to make, usually. You cannot avoid it. And it makes things uncanonical. which looks like a drawback, but we'll also see that it is a virtue for this for the Quiver setup. We make the choice of a character of the group. Make the choice of a character chi, which is just a homomorphism of algebraic groups from G to the multiplicative group C star. Your typical reductive group is GL, and then your typical character is the determinant, or some power of the determinant, positive or negative power of the determinant. Yeah, that's the typical character we think of. So using this choice of a character, we slightly generalize the notion of an invariant. If you remember last time, to form the quotient, we looked at invariant functions, and now we define a relative version of invariance with respect to this character, which is just called semi-invariance. So let me define the ring of chi semi-invariance. So the ring of invariance we denoted last time by CV, the ring of polynomial functions on V, G about G for G invariance, and now we just put an index chi. And we define it as the following linear span. It's defined as the span of all polynomial functions which have the following transformation behavior with respect to the group, namely f of G times V. So that would be the condition for invariance. F of G times V equals F of V. But we twist this invariance a little bit, namely we twist it by some power of the character. So F of G times V equals chi of G to the n times F of V. So this should hold for all G in the group and for all V in the vector space, and it should hold for some non-negative m. For some non-negative n. So and we take the linear span of all these. So what's this? So first of all, this power n attached to a certain function f here, we call the weight. Let me just quickly call this the, maybe with color. Yes. Let me call this the weight of n. So why do we only have to take the linear span of such functions? Well, you can quickly see if you multiply a function of weight n and a function of weight n prime, you get a semi-invariant function of weight n plus n prime. Yeah? So that in particular means that this is even a graded ring, naturally graded by the weight here. So that's the graded ring of chi semi-invariance. And you know automatically what the degree 0 component of this is. Namely, the degree 0 component means you have the 0 power here, so this vanishes. And so as degree 0 component in this graded ring, you have the ring of invariance, which we considered last time. So this is a generalization of the ring of invariance. All right, so that's the key definition to somehow slightly relax the notion of an invariant. And now we can define what are semi-stable points for our group action. Namely, let me define V chi semi-stable as the set of all points in our vector space for which some positive weight semi-invariant doesn't take the value 0. It's non-zero for some semi-invariant function of strictly positive weight. If we don't require this strictly positive weight, then this definition would be empty, because otherwise you could just take the constant function 1, which is definitely invariant, but and nowhere vanishing, so this definition would be void. So that's the semi-stable locus for this group action, and that's now the pure magic of Mumford's GIT. This automatically rules out all the bad orbits, and all the orbits in there are the nice orbits. That's it. So now we form the quotient, in the following way. We take the approach, of this ring of semi-invariant functions. This is fine because we automatically have a graded ring. And for any such graded and in fact finitely generated by Hilbert's theorem ring, you can form the approach, which is a projective variety over the spectrum of the degree 0 part. We'll come to this later. And this is in fact a nice quotient map. So I claim that this thing, which we'll now call the Mumford quotient, so it's the quotient of the semi-stable part by the group G. This is a quotient which parameterizes, again, the closed orbits for the group action, but now not the closed orbits in the whole of V, but only the closed orbits in the semi-stable locus. So this is a quotient which parameterizes closed orbits of G in the semi-stable locus. So that is more or less the essence of Mumford's GIT for linear actions on one blackboard. I really tried to optimize this. And if you compare this to the construction last time, it's really an analogy. Last time we constructed a categorical quotient. You defined using some universal property, and it parameterized the closed orbits of G in the whole of the vector space. We realized in many cases this is not at all interesting because we have really small and bad closed orbits like the origin here. And to get something better, we first remove the bad orbits, and this is done by this definition. We slightly generalize invariance to semi-invariance and just look at the points where some semi-invariant doesn't vanish, and then we're done. That's the claim of Mumford's GIT. All right, just as a little reality check, let's do this in the two examples which I wrote down yesterday. Well, not precisely yesterday, last week. In the last talk. Okay, so these were the two group actions. In both, we had the dilation action on the plane, and we had the action by weights 1 and -1, whose typical orbits are hyperbolas, but which has bad orbits being the origin, pointed x-axis and pointed y-axis. So let's choose a character. Character is just a group homomorphism from C star to C star. Let's take the identity. So the determinant of a 1-by-1 matrix. Yeah. Okay. So and now we can work out what are the semi-invariant functions. So here in this case, the ring of semi-invariant functions is generated by the coordinate functions x and y. Both x and y are semi-invariants with respect of weight 1, because both coordinate functions x and y transform with weight 1. X transforms with t times x. Yeah, that's the definition. So this we consider now as a graded ring. And as quotient, we take the approach of the graded ring. And the approach of the graded of the polynomial ring in two variables with standard grading, x and y being of weight 1, is just P1. Yeah? So the approach of this is just by definition P1, which is precisely what we want to have as a quotient, because we want to parameterize this beautiful family of punctured lines through the origin naturally by P1. And what is the semi-stable locus? That's the whole plane minus the origin. Why? Well, a semi-stable point is a point where some positive weight semi-invariant does not vanish. So the semi-stable locus is all the points where either x or y doesn't vanish. And that's everything except the origin. That does the trick. All right. So check. That's precisely what we want. What happens in this example? In this example, we have already, I've already remarked last time that all these hyperbola are somehow nice orbits, and then there are these bad orbits, origin, pointed x-axis, pointed y-axis. And at some point, we have to make a choice whether we want to remove the x-axis or the y-axis. And let's now see how magically the choice of a character does the trick for us. Namely, if we take the character identity, then the graded ring of semi-invariants is generated by, well, first of all, there is an invariant function, xy. Xy is definitely invariant. If you plug in the rule for the transformation, you see it's invariant. And then x is of degree 1. So we have a graded, so we have again a polynomial ring in two variables, but now with a different grading. This has degree 0 and this has degree 1. And now the approach is the affine line. Yeah? We have a non-trivial degree 0 part in this graded ring. And so the approach of this graded ring is A1. And the semi-stable locus is all the points in the plane where some positive weight semi-invariant does not vanish. And the positive weight semi-invariants are generated by x. So it's all the points where the x coordinate does not vanish. So it's C2 minus the y-axis. You can make another choice of the character here and take the character which maps T to T inverse, and then you get the other possibility. You get the same approach, but then you remove the x-axis. Yeah? So all the question of what are good, what are bad orbits for the group action is automatically given to us by the choice of a character in this Mumford GIT. Yeah? So that's a really nice solution. All right, so now let's apply this to the Quiver situation, to the Quiver action of the base change group GD to the representation space RD. And then we have to do several translations. Namely, we have to find out what is this choice of a character, what means semi-stability. That's a lot more work than last time. But luckily for us, it was all done by Alistair King in a paper in 1994. And I will not show you this translation step by step because it involves some more ingredients, the Hilbert-Mumford criterion, the numerical criterion. But I will just show you the final result, which we get. And then we will see that it is somehow a direct analog of this story. Yeah. So that's the point I would like to make. So first of all, the choice of a character is the choice of a stability function. Of a very simple stability function, but which is enough to produce all the beauty of categorical stability, like it is known by now. And I will also show you how it comes up naturally. So let me summarize. So apply the Mumford GIT to our group action GD on RD of Q, which is the group action for which the orbits are precisely the isomorphism classes of Quiver representations. So this is the theorem, and most of it is from Alistair King's paper. In the final part will be a theorem by Schofield and Vandenberg. So from the very beginning, we have to make a choice, like the choice of a character in Mumford GIT. So we choose a stability theta, which for us is nothing else than a linear function on on the free abelian group in the vertices of the quiver. Choose this. And this choice is crucial for the whole story, and it is subtle. If you do the wrong choice, all your moduli spaces will be trivial, like empty. And finding the right stability is often very non-trivial. I will tell you something about the story when we look at the stability space. But for the moment, let's just say everything that follows works for arbitrary choices of theta. It might be just trivial. Okay, so make this choice of a theta. And for people knowing this whole story, I will now consequently work with slope stability. I will not assume that theta vanishes on a given dimension vector D, because I want to emphasize again the categorical aspects of stability. So let me derive a slope function from this. So after this choice, we define the slope of a representation. So slope mu of a representation V is now defined as, well, apply theta to the dimension vector of V. The dimension vector of V is this whole vector recording the dimensions in a quiver representation, and we can apply this linear function theta to it, and we divide by dim of V, which is the total dimension of the representation. This is not totally canonical. You can replace dim by any other strictly positive functional on representations, but just for simplicity, let me make this choice here. So that is the slope, and is obviously only well defined if your representation is not zero. All right, that's the slope of a representation. This theta is the choice of a stability. And now let me make some definitions on stability, so semi-stability and variance. So a representation V is called theta semi-stable if and only if the following innocent little condition holds. If you look at any subrepresentation of U, the slope will weakly decrease. So mu of U is less than or equal mu of V for all non-zero non-zero proper subrepresentations. So that will be ultimately the translation of this notion of semi-stability, which we have seen in the general theory. So some positively graded, positively weighted semi-invariant is non-vanishing. And that translation is quite a long story, but let's just believe that this is true. There's a stronger thing, namely V is called theta stable if and only if you have a strict inequality here. And the final notion we need is what it means for V to be Pauli stable. This I need to say exactly what our moduli space parameterizes. V is called Pauli stable if it is isomorphic to a direct sum of stables, all of the same slope. V is isomorphic to a direct sum of stables of the same slope. All right. So these are the important definitions. And now we will put these definitions into the geometric context first, what they give us for the construction of moduli spaces. And after that, after formulating this whole theorem, I will look at these notions from a more categorical point of view. Yeah, and then we have again two different point of views which we can play against each other. Okay, so given this definition, then, well, for an appropriate choice of a character on the group GD, we have the following. This is nothing bad. It's just a bit complicated to write this formula down. But I mean, from this theta, you can immediately produce a certain character on this base change group GD, such that the following holds. If inside our vector space Rd of Q, the vector space on which our base change group acts, if we then look at the semi-stable points with respect to this character, it is precisely the set of all representations which are semi-stable in this sense. That's the first step. Yeah? So this completely invariant theoretic notion of semi-stability, that a certain semi-invariant is non-vanishing, translates into this representation theoretic notion. And that requires the use of the Hilbert-Mumford numerical criterion, which is quite non-trivial, and it requires some work. But that's the first part of the theorem. Okay, so now we know from the general theorem that we can now form the quotient of this subset by the structure group, and that it parameterizes the closed orbits in here. And now this part of the theorem will be very parallel to the story above. So second part is now, that's the first part of the theorem. Second part is we define the moduli space of theta, while I write down semi-stable, which is not really true. But let me just use this notation. So we take the quotient of this set of semi-stables by our group GD. And now this parameterizes the closed orbits in the semi-stable locus. And these closed orbits in the semi-stable locus are precisely the polystable representations. Yeah? So this moduli space, so this is an algebraic variety. And I can delete the examples. Is an algebraic variety parametrizing isoclasses of theta polystables of dimension type D. So, and this perfectly matches the first part of the theorem here. Here we had the semi-simple moduli space of semi-simples. It is just the usual invariant theoretic quotient, but it parameterizes isoclasses of semi-simples. And the roles of semi-simples is now played by the theta polystables. And we'll see in a few minutes that this is indeed not only an analogy, but this really generalizes this theorem. So the next part of our original theorem was about geometric properties. The moduli space we constructed last time was irreducible, normal, affine of known dimension if there exists a simple representation. And we have a perfectly analogous result here. And after formulating this theorem, we can already have a break. Yes, we should. So this moduli space of semi-simples, in general, it's neither affine nor projective, but it admits a projective morphism to the moduli space of semi-simples, projective, and this is affine. So here you see that this is a quasi-projective variety, and we can clearly separate the affine and the projective direction. The affine part comes from the moduli space of semi-simples, which we know is only non-trivial if we have oriented cycles in the quiver. And the projective part is in the relation between these two. So it's projective over this, and it is of dimension, well, the same as in the affine case. If there exists a stable. So we have, again, an expected dimension, and this expected dimension is the actual dimension if there exists a stable. And again, it's irreducible and normal. All right. So that was the theorem of Alistair King. And now to the Schofield-Vandenberg part. In the theorem last time, we had explicit in principle, we can find explicit coordinates by traces along oriented cycles. And here again, there's a general result that you can find coordinates for these moduli spaces, always by considering appropriate determinants, determinantal semi-invariants. Yeah? So out of the matrices in the Quiver representation, build some square matrices in some funny way. And you have to get some intuition for that. And if you have square matrices, you can take the determinant, look at its weight as a semi-invariant, and then you can combine all these determinants in a way so that you get semi-invariants of the right way. And in principle, all semi-invariants can be constructed by this. All semi-invariants are given by determinants, by appropriate determinants. I will give you one example after the first break. And okay, so that's time for the first break.
Okay, thank you, Markus. There's one question in chat. So in point 2 of the second theorem, you used the quotient by so double line quotient by GD, but I don't think we've introduced the notation officially yet.
You mean here?
Yeah, I think that's the question.
Okay,
yeah.
so I should emphasize the character again, or what? No. Okay. So
the notation
what is the question?
I think the question is, what does this notation mean? Because you haven't said that this is proch of the.
Yes. Yes. Right. Let me continue with the tradition, answering the questions in blue. So the general definition was that this quotient of the chi semi-stable locus by the group.
Markus, the blue on white, this is very hard to read.
Is the approach of this graded ring of semi-invariant functions.
Okay, so this is very hard to read because you wrote on what you just erased.
Yes, that's true. Definitely. Okay, let me do it again. Yes. Okay. Please remind that this was Schofield and Vandenberg. So by the general theory, inside the vector space, we have this locus of semi-stable points, and we want to form the quotient by GD, by some group G, and this is the approach of the ring of semi-invariant functions. This graded ring, sorry, the graded ring of semi-invariant functions. Yeah, and that was the main content of the first theorem, that this approach of a ring of semi-invariant functions is a space is a variety parameterizing the closed orbits of G in this semi-stable locus, so in the set of all good orbits. Yeah, and that's precisely what we apply here for an appropriate choice of the character, which I haven't told you. Yeah, but then you take the set of semi-stable points, which is precisely semi-stable points in this representation theoretic interpretation. And then again, you take this quotient by GD, which is this approach of semi-invariant functions.
Thank you. There are no further questions in chat.
I want to ask one question.
Oh, yeah, go ahead. Go ahead.
Ah,
Jens.
sorry.
Yes, please.
Yes, so I'm Jens, and I wanted to ask the following thing. So somehow this quotient relies on having characters around. So we had lots of characters because we had all the determinants. What happens if you restrict G to just SL, for example?
Ah, okay. Yes, yeah, yes, of course. You can just do the following. In the very definition of our group action, you could replace the GD, which is the product of GLs, by the product of the SLs. Yeah. Then you have a much larger quotient because you have no choice of characters. And you always have interesting quotients. And it's definitely very interesting to look at this quotient. Only problem is, what does it parameterize? Yeah, because, well, our original idea was to really parameterize things up to base change, and the natural base change group is GL.
Yes.
So what it parameterizes is something like Quiver representation with a volume form attached to any vector space. Yeah, because, well, the SL is just the group preserving this volume form. You could invent this notion and then study these quotients, and they are related to studying Quiver representations with volume forms. That's perfectly possible. I just wanted to stay very close to the original problem of classifying Quiver representations up to isomorphism, and then I just cannot avoid going through GIT and making this choice of a character. But we will see that this choice of a character is actually not that awful, and that it gives us, so it's not a bug, it's a feature. It will give us a lot of beautiful things to do by changing the character. Yeah, and this will be lots of fun in the next talks. So let's see what happens.
Okay, sorry, yes, thank you.
That's one question in the audience. Okay. Yeah. So the question is, I mean, I'm not using the theta semi-stability, but the slope semi-stability. Well, note that the slope of a single representation only depends on its dimension vector. Yeah. Here's the dimension vector, and the total dimension is just the sum of the entries in the dimension vector. So the slope of V is constant along the whole R of D. Yeah. And whether it's semi-stable or not, that's just really in the sub-representation lattice of V. Yeah, but the slope doesn't really discriminate representations in a fixed representation space. Yeah, so the only virtue of the slope semi-stability is that I can speak about all representations being semi-stable or not at the same time. Whereas in the original theta semi-stability, you always have to find a theta which is 0 on a given dimension vector, and you can only speak about representations of a fixed dimension vector. Yeah, but to fruitfully combine the geometric and the algebraic approach, I want to have some semi-stability at the same time for all possible representations, and this is the reason. Yeah, so it's really not a big deal. It's just a little modification which you have to make to the theta. Just rescale it so that for a given D, it's trivial on the scalar subgroup.
There's one further question in chat, but I think that's a good question for at the very end, because it's a very cursory question. So I suggest we continue now.
All right. Okay. Yes. So now that we have this general theorem, we could start working out examples. The technical problem I have is that working out any single example, really working out what is stability, how do you find enough semi-invariants, requires long calculations and will really take a long time. So I will just sketch two classes of examples very briefly, because I will come back to them in the applications of moduli spaces later. And but I can't give the details of how to do the stability analysis on and so on, unfortunately. So I have to be a bit sketchy on that. So yes, okay. So I will do three classes of examples. The first example is, which is perfectly valid for what I developed up to this point, is to choose theta as 0. That looks really trivial, but it's perfectly allowed. And let's just see what it gives. That's very instructive if you haven't seen it before. As a second example, let's then look at the generalized Kronecker quivers, and as third examples, subspace quivers. Okay, so some brief examples. Example 1, what if theta, our chosen functional, stability functional, is 0? Well, if theta is 0, then the slope function is identically 0. So there's no slope at all. So what does this mean for this definition, semi-stable, stable, polystable? So what is 0 semi-stable? 0 semi-stable just means the slope is weakly decreasing on subrepresentations. This condition is totally trivial because the slope is identically 0 anyway. So 0 semi-stability holds for all representations. Okay. So what about 0 stability? Well, a representation is 0 stable if the slope strictly decreases on non-zero proper subrepresentations. That's something the slope cannot accomplish because it's always 0. So when does this happen? Well, okay, so the slope cannot strictly decrease, so we just have to avoid having subrepresentations. Yeah? So 0 stable means simple. Zero stable representations are the simple representations. Okay, and then we know what is 0 polystable. A polystable is a direct sum of stables of the same slope. Well, the stables are the simples, and they are all of slope 0. So a polystable is nothing else than a semi-simple representation. Aha. So now we see the perfect analogy to what we did last time. Last time, we managed to parameterize in the moduli space the semi-simple representations. And now we parameterize the polystables. This I erased. This quotient is an algebraic variety parameterizing polystables, theta polystables. And we see that if we specialize theta to 0, then we get back our original moduli spaces parameterizing the 0 polystables, which means the semi-simples. Yeah. So you see, our theta stable situation is really a generalization of our original moduli spaces. For theta equals 0, we get back what we already had. Yeah. So you see in this case that the moduli space of 0 semi-stables is just the moduli space of semi-simples we already knew. Perfect. Second example, let's look at the generalized Kronecker quiver. So it has 2 vertices, 1 and 2, and m arrows. And well, things get interesting if m is greater or equal 3. Yeah, if you look at the list of linear algebra problems, from the first talk, things get interesting if you parameterize 3 or more linear maps up to simultaneous base change in the source and in the target. Okay, let me write the dimension vector as d1, d2, and let me make the choice theta of d1, d2 equals d1. That looks a bit arbitrary, but in fact, almost all choices of theta for this Kronecker, generalized Kronecker quiver are equivalent. There are basically 3 equivalence classes of stabilities. 2 of them give something trivial, and 1 of them gives something interesting, and that's the representant for this interesting class. All right, so then a representation which is given by 2 vector spaces and a bunch of M linear maps. It is theta semi-stable, if and only if the following criterion holds for all non-zero proper subspaces of V1. The dimension of the sum of all the images of the subspace U1 is greater or equal for semi-stability and strictly greater for stability than d2 by d1 times the dimension of U. So that's the first thing you have to do in any concrete situation if you want to compute a quiver moduli space. First, perform a stability analysis. What is it in linear algebra term that makes the representation semi-stable or stable? Because only then you know what you will ultimately parameterize. Yeah, and here, well, this means the linear maps Fk are somehow not too parallel. Yeah, if they would be parallel, like all the same, then you would never manage to generate from one given subspace a very large sum of all the images. But if somehow the linear maps go in different directions, then from a single subspace, by taking the sum of the images, you can produce quite large subspaces in the target space. And what quite large means is made precise by Mumford, and it is precisely this inequality, which is not too natural from the linear algebra point of view, but it just automatically arises from the Mumford GIT point of view. So that's the representations we can ultimately parameterize. But even for this quiver to actually coordinatize the moduli space is extremely hard. Yeah. So the only good coordinatization I know is if one of the 2 spaces is one-dimensional. This is not much. Okay, so as a particular example, if the space V1 is one-dimensional, so it's just C, then I claim that the moduli space for this dimension vector M1, M2 of theta semi-stables for this quiver is isomorphic to the Grassmannian of k-dimensional subspaces, of d2-dimensional subspaces of an m-dimensional space. This is quite a prominent variety, and we can really quite easily see this isomorphism using a very low-dimensional example of this last part of the theorem. The last part of the theorem said that we can generate or can get all the semi-invariants from appropriate determinants. And this is one particular case in which you can actually see all these determinants. And if you see the determinants, then you see that the moduli space is a Grassmannian. So I think this is also a very instructive example to work out in all details. So namely, let's write down a representation. You have a one-dimensional vector space here, a d2-dimensional vector space here, say C to the D2, and we have M linear maps. So linear maps from one-dimensional to a D2-dimensional space. So these maps are just represented by column vectors of length D2. Say vectors V1 to Vm. Arrange them in a matrix. V1, Vm. That's a D2 by M matrix. Now, if you have such a matrix, how can we easily produce square matrices, determinants of square matrices? Well, we could just take the maximum minus of this matrix. Yeah, assuming for a second that M is greater or equal to D2. All maximum minus of A are in fact theta semi-invariant functions in this case, and they generate this whole graded ring of semi-invariants. And then, of course, between the maximum minus of a matrix, in general, you have relations. Yeah, they are not independent coordinates. And the relations are the Plücker relations. Yeah, so they satisfy Plücker relations. And so what you get at the end is a map from this moduli space, which we want to determine, a map into a large projective space, namely projective space of dimension, well, as many minus as you have, -1. So the dimension is M choose D2 -1, D2 element subset of an M element set -1. So this map is the collection of all maximal minus. And the image of, so this is automatically a closed embedding. And the image, well, the image of the Plücker embedding is the Grassmannian. That's how you typically define it. Yeah? So this moduli space is the Grassmannian because it is defined as the image of the Plücker embedding. There are different ways to see that this is a Grassmannian, but this is a nice one because you can really apply this Schofield-Vandenberg very explicitly, and you can really see appropriate determinants which give you generating semi-invariants. Okay, a third example would be points in projective space. Yes.
Markus, before you continue, there's one question about your first example. Does one have to change the definition of semi-invariance for zero stability, or does the definition work the way it was defined? Because you took the subring generated by sim.
Well, yes, that's a good one. Let's see. Our character would be not the identity, but the constant function 1. Yeah. Okay, so let me write this down. Yes, that's a very good point. So if theta is 0, then actually all these characters chi theta, which I haven't written down, but which are important to define, are just not the identity, or it's just a constant function 1. And now let's look again at the question, what is a semi-invariant for this? Semi-invariant for this is a function f which transforms with along this rule, right? That was the definition of a semi-invariant. Now, in our case, where the chi, the character is trivial, so it is constantly 1, we can replace this by 1. And then you see that any invariant function is automatically a semi-invariant for any weight. in particular for any positive weight. That's a bit cheating, but I think the definition which I wrote down works again here. Yeah, because the semi-stable locus should be everything. All representations are semi-stable here for this choice. So every point should be semi-stable, and that's indeed true, because a semi-stable point is a point where some semi-invariant of positive weight is non-vanishing. And here, well, you could even just pick a constant function, 1. It would be a semi-invariant for any positive weight n. So in particular, it's a semi-invariant for some positive n, and it's non-vanishing on any point. So I think the definition is really fine, even in this trivial case, although it looks like cheating.
Yes, there's one follow-up question. Do we get a useful grading in this way?
Sorry?
Do we get a useful grading in this way?
Nope. No, I mean, what? Okay, so in the case where theta is 0, you shouldn't get anything else than the usual quotient, which you always get. Yeah. So your approach should just be your spec. There's nothing to expect. Yeah. I mean, we cannot expect any new information just from using a new language. We have to do something concretely, and here we're not changing anything. Yeah. So there can't be any new information inside. So the approach is just a spec in this case.
Yes, thank you.
Okay.
That was it.
So let me skip the third example. I will postpone this to when I need it, because I want to finish today's lecture with the algebraic aspects of stability, which will be very important when we do wall crossing on Wednesday. So algebraic or categorical aspects of stability. So we have chosen this the stability theta, and we have associated to it a slope function. And then you can do the following definition. So algebraic aspects now refers now to the category of representations. Remember the notation rep-CQ? That was the abelian finite length C-linear category of complex Quiver representations, finite dimensional complex Quiver representations, like we defined in the first talk. And now let me put a new here. And this I define as the full subcategory of the category of all Quiver representations, the full subcategory of the objects which are semi-stable representations of a fixed slope of theta semi-stables of slope mu. And now I view this mu just as a rational number. Yeah. So the slope, as I already told you, only depends on the dimension vector of the representation. Yeah. And so for all the dimension vectors where the slope assumes a certain value, we just look at the semi-stables and we take the full subcategory. And now the nice thing, that is one of the algebraic aspects, is that this is automatically an abelian subcategory. Is an abelian subcategory. So for any map between semi-stables of the same slope, the kernel, the co-kernel, and the image are automatically again in this subcategory. This subcategory is closed under taking direct sums, even extensions, arbitrary extensions. So it inherits from rep-C of Q a complete abelian structure. So it's a very, very nice subcategory. And it's again a finite length category in the sense that composition series, relative composition series in the subcategory are of finite length, well, because everything is just finite dimensional vector spaces. Yeah, so that's also clear. The difference is that even if your whole representation category has only finitely many isoclasses of simples, for example, if your quiver is acyclic, in the subcategory, you might have lots and lots of simples, because the simples are precisely the stables. Yeah? So it's an abelian subcategory, and the simples in here are the theta stables, and the semi-simples in here are the theta polystables. And that explains why this notion of stability and polystability are natural, because it's just a relative notion of simplicity and semi-simplicity in these abelian subcategories. Well, okay, so what we now have is inside this category of representations, we have a family of abelian subcategories indexed by the rationals. So how do they behave with respect to each other? Well, first of all, in one direction, you have no homomorphisms. So it's a directed decomposition of the category. So we have no homomorphisms from a semi-stable of slope mu to a semi-stable of slope nu. So this is identically 0 if mu is strictly bigger than nu. And the third part is, so this is not only a certain directed series of subcategories in the sense that you have homs only in one direction, but it is really a directed decomposition of the whole category, which means you can filter any representation of the quiver canonically such that all the subquotients are in these abelian subcategories. So for all representation view, there exists a unique filtration 0 equals V0 in V1 and so on in Vs equals V, such that first all the subquotients Vi by Vi minus 1 are semi-stable. And you do this in a certain ordering. So the slopes of these subquotients are strictly decreasing. So, and this is something which you do not encounter in the classical theorems of module theory, like Jordan-Hölder theorem or the Kohl-Schmidt theorem. Jordan-Hölder tells you you can filter any representation such that the subquotients are simples. But this filtration is far from being unique. You only know that the isomorphism types of the subquotients are unique up to permutation. But here, even the filtration is unique. And in the Kohl-Schmidt theorem, you can filter, well, you have a split filtration by direct summons into indecomposables. Again, you have no uniqueness. But here you have uniqueness of the filtration. And in fact, if you index the filtration by the rationals, then this filtration is even functorial. Yeah, but you have to do a little trick and index the filtration by the rationals, namely by all the slopes. And then this filtration is even functorial, a completely natural functorial filtration. So that is called a Harder-Simon filtration. So these are the three main algebraic properties. And if you have ever read about Bridgeland stability space, then you will recognize all this. So these algebraic properties of stability, which we motivated just from the geometry of this group action, these constitute the main axioms for a Bridgeland stability on a triangulated category. Not completely. There are some technical issues which are, of course, very subtle, but this is some of the essence. Yeah. So you have a canonical directed decomposition of the whole category into the subcategory. And for the subcategories, we have a geometric parameterization, at least of all the semi-stables. And on Wednesday, we will see that the existence, just the pure existence of this Harder-Simon filtration is equivalent to what is now known as a wall crossing formula for motivic invariance of Quivers. And this I will explain on Wednesday. And I think, yes, time is over. Thank you very much for your attention.
Thank you very much. Let's clap in chat for Markus. So there is one question in chat asking, in which extent does the length of the filtration depend on the choice of theta?
The length of the Hardenauer-Simon filtration.
I think so, yeah.
Oh yes, I mean you can have you can easily have situations where for one choice of theta you have a semi-stable representation, and if you have a semi-stable, then the length of Hardenauer-Simon is 1. It's just 0 inside the semi-stable. That's the filtration. But then you modify the theta, and it's no longer semi-stable, and it may break into several parts. And I think I don't know of any a priori bound for the length. So I think a semi-stable for one stability might have an arbitrarily long Hardenauer-Simon filtration for some other theta. Yeah, I guess it could be arbitrary.
Okay, thank you. Are there any other questions that people want to ask now?
There was one question apparently which you wanted to postpone from the halftime break.
Yes, we can ask it now.
Okay.
So this question, let me phrase this into a coherent sentence. Would we replace polystable by S-equivalence classes if we were to look at semi-stables for coherent sheaves? But maybe
okay, yeah, yes. So in the theory of moduli spaces of coherent sheaves, or for example, vector bundles on smooth projective curves, there is this notion of S-equivalence, and let me briefly explain that this S-equivalence classes are nothing else than just isomorphism classes of polystables. So if you look at this, if you look at the notion of S-equivalence in moduli spaces of coherent sheaves, it is usually defined as follows. Okay, let me rephrase it for the Quiver setup. So here's the category of representations of the Quiver, and assume you have a full abelian subcategory. And application will, of course, be to these abelian subcategories of semi-stables of fixed slope, which we have seen. Then we can call V and W S equivalent if the following happens. Well, it should be an abelian subcategory of finite length. And then if V and W are objects in this category, let me switch blackboards. I'm just making up an ad hoc definition, which I think matches the definition in the coherent sheaf literature. So two objects V and W in this coherent sheaf, in this abelian subcategory are called S-equivalent if the following holds. Well, because this category C is finite length, you consider relative Jordan-Hölder series, composition series. And so it has how should I write this? Okay. You take the associated graded. Let me write it like this. For this object V, you have a relative Jordan-Hölder series because it is an object in the subcategory C. And then you can take the associated graded, just the direct sum of all the subprojects. And Jordan-Hölder tells us this is unique up to isomorphism. You can do this for the other representation. And then S-equivalence is just saying that these associated gradients are isomorphic. Yeah. Okay, now in any S-equivalent class, you can just take an object which is just a direct sum of simples. S-equivalence class contains a unique, up to isomorphism, direct sum of C simple objects. Yeah, because if you have a direct sum of C simples, then the Jordan-Hölder filtration is just the split filtration and the associated gradient is itself. Yeah. Okay. And so that means having a moduli space parametrizing S-equivalence classes is the same as having a moduli space parametrizing these relative semi-simples, these direct sums of simples with respect to the subcategory. And in our Quiver situation, this would just mean the obvious notion of S-equivalence just reduces to this notion of polystability, because in any S-equivalence class, you have a unique polystable.
Okay, thank you. Are there any other questions that we want to ask now? Otherwise, I can stop the recording. Yeah, there is one question. Kaveh, go ahead.
Thank you. So I was wondering if I could ask about this clicker embedding that you neatly use in order to recover the Grassmannian as a kind of theta semi-stable variety.
Yeah.
If I'm not mistaken, correct me if I'm wrong, but there's this result of Lutz-Hille that proves that literally you can recover any arbitrary nasty projective variety as a semi-stability condition. Is that like through the same line of argument, or?
Let me comment on this because it's a comment I wanted to make anyway. So, well, so the story so far does not really rely on the setup of representations of a quiver, arbitrary representations. You could do the same thing for representations of a quiver bound to certain fixed relations. Yeah. The difference is that then the moduli spaces you get are quite arbitrary. So let me somehow, yeah, let me explain this with a few lines. Yes, so remark. I have to just write a few sentences about that, somehow to make the logic clear. So first of all, you could define, not only you could, but one does. Given a quiver with relations, Q, and then an appropriate ideal in the path algebra. The same method defines a moduli space of theta semi-stable representations of a quiver with relations. Namely, so this is actually quite easy. So how do you do this? Well, you first forget about the relations. Namely, you start with your whole, what did we do? We started with our whole representation variety. Inside this, we only looked at the semi-stables. And then we have a quotient map to this moduli space of semi-stables for the quiver. Now, inside this whole representation space for the big quiver, you have, as a closed subset, those representations which fulfill the given relations. Yeah? These are all representations fulfilling the relations. And what you just do now is you just take the image of this subset, this closed subset, under the quotient map. You just take pi d of all the representations fulfilling the relations. By general properties of quotient maps, you get automatically a closed immersion into the moduli space. And this thing here, this image, you define as the moduli space, which we want. So this is the formal definition of that moduli space. Yeah? So it's really, you don't have to go through the whole story again. You just do the whole construction in the Quiver without relation setting, and then just take this closed subset, and this gives you moduli spaces for Quiver with relations. You can study them, of course, but for the application which I have in mind, these are not the right, the things don't work in this generality for several reasons. The main reason being that you can construct any projective variety, even for a very small dimension vector. And I think that the Quiver which Lutz Hille took is just somehow a long chain of Kroneckers. So any projective variety appears as such a moduli space of semi-stables, Qi, for Q being something like a chain of Kroneckers, and for D being even the dimension vector which has ones everywhere. Yeah? And actually, one has to find some clever construction for this, but somehow morally, it's not too surprising that this happens. Namely, think about the general problem, parameterizing representations of some ring or algebra. Yeah? Forgetting about quivers, just we want to parameterize representations of a ring. Well, any affine variety is, by definition, a moduli space for one-dimensional representations of its coordinate ring. Any affine X is a moduli space for one-dimensional representations of its coordinate ring. Why? So what is a one-dimensional representation of a, well, this is the coordinate ring, just the usual affine coordinate ring. So it's a finitely generated commutative C algebra, reduced C algebra. What is a one-dimensional representation of it? Well, a one-dimensional representation is just the factor by some maximal ideal. And by the Hilbert-Nullstellensatz, any ideals in here have one-dimensional, any maximal ideal has one-dimensional quotient. Yeah? So the moduli space is of one-dimensional representations is by definition a moduli space for the maximal ideals in the coordinate ring. And the moduli space for maximal ideal, that's just the spectrum of maximal ideals of the coordinate ring. Yeah? So this is tautological. Any affine variety is the moduli space of one-dimensional representation of its coordinate ring. And you can push this further, passing to projective varieties, and then taking moduli spaces for essentially one-dimensional representations of a long quiver. And in the relations, you encode the defining relations of the projective variety. Yeah. Okay. So final point of that's actually a long answer. So the final point is that a point which I wanted to make in the next talk. If your dimension, no, if your dimension vector is indivisible, just meaning the GCD of all the entries is 1. And if theta is somehow sufficiently generic, so it avoids some finitely many bad hyperplanes, then the moduli space of theta semi-stable representations of Q is a smooth variety. And from the point of affine of algebraic geometry, smoothness is obviously desirable. So if you have a quiver with relations, this is usually wrong, almost always wrong. Yeah, but whenever you have a very special class of relations, for which you can prove, usually by homological reasoning, that your moduli spaces are smooth in a sufficiently generic situation, then you have found a really good class of moduli spaces. So apart from quivers without relations, this works for, so if you put relations in here, this usually works for pre-projective algebras or for Jacobian algebras by some Jacobian algebras with respect to some potential. So, and that means you cannot put arbitrary relations there, but the relations should somehow be so special that you have some homological information about your category. Yeah. So the path algebra, the category of representations is nice because it is hereditary. We haven't treated this aspect so far, but we will on Wednesday. If you consider a double quiver with pre-projective relations, then typically you are in a 2 Calabi-Yau situation. If you consider the Jacobian algebra with respect to potential, then typically you are in a 3 Calabi-Yau situation. So you need some very good homological duality, say Calabi-Yau. And then you can hope for smoothness of your moduli spaces of quivers with relations. But if your relations are arbitrary and you don't have precise control over the homological algebra of your category, then you cannot expect smooth moduli spaces, and then you cannot expect these moduli spaces to have any nice structure. That was the very long answer to your question.
Okay, thank you very much, Markus. I will now stop the recording, and then we can continue discussing a little bit.
All right.